Hello everyone, in this video we are going to discuss the different methods which are used to calculate the runoff. So let's start. So the first method is to calculate the runoff from the given rainfall. Now, it was already stated that the rain which is falling on the ground in the form of the precipitation, that is first of all intercepted as the interception losses. So these are usually by the trees, or in general we call that as the vegetation or any other obstruction which is in the path of the falling raindrops. So that will be intercepted by them. Then rest of the water which is reaching the earth's surface, that will be moving on the earth's surface and it will be filling up these depressions. So if the water is flowing and such depression is made, so the first of all water will be filled up in this depression, and when this is at the same level, then only the water will move ahead. So this type of storage of water, that is known as the depression storages. And rest of the water that is percolating and is used in removing the soil moisture deficiency. Now, after completing all these parameters, the rest of the water that will be flowing as the stream flow, or rest of the water may flow as the groundwater accretion. Now the amount of precipitation which is falling, it has to fulfill all of these needs, and these are termed as the initial basin recharge. That means the catchment area that is recharged by the water which is falling in these form, and it is denoted by capital L. Now it includes this P value, SD value, and the rain which is absorbed by the soil moisture deficiency. Now what is this P? That is usually represented for the interception, and the more suitable denomination will be the PJ. Then SD is the depression storage and rest is the soil moisture deficiency. Now initial basin recharge is therefore the water which is withheld within the basin, that means within the catchment area, before the precipitation starts contributing to the stream flow or to the groundwater. Before these two things happen, whatever water is consumed, that is termed as the initial basin recharge, and that is denoted by this capital L. Once this initial recharge is filled up, the water infiltrate into the ground as the groundwater accretion, which is denoted by capital G, and the excess water or the remaining water that will flow as the direct runoff. The total precipitation therefore can be represented as, out of the precipitation, some part is consumed by the initial basin recharge, rest is percolated into the ground as the groundwater accretion, and the remaining one that is flowing as the runoff. So we are concerned with this Q value. So this can be written as Q is equals to total precipitation minus initial basin recharge minus groundwater accretion. That is the runoff, and that is how we calculate the runoff from the given rainfall. That was the first method. Moving on to the next one, that is the calculation of the runoff depth by using the runoff coefficient. That means what we do, the volume of the runoff, that means in how much cubic meters the water has fallen and how much of that water is contributing towards the runoff, is calculated approximately by using an equation which is of the form Q is equals to Kp. Here what we are doing, this P is the precipitation, so we are directly relating the precipitation to the runoff by a constant value which is denoted by K, which is having a value less than 1 or at the most is equal to 1. So this K value is less than equal to 1, and that should also be true because only a portion or the fraction of the precipitation is contributing towards the runoff. Rest is absorbed by different activities. So that's why this K value should always be less than 1. Now this K value that depends upon the imperviousness of the drainage area. If the perviousness is more, that means the water can percolate through the earth's surface, then the lesser volume will be available for the runoff. Therefore, the value of the K, it increases with increase in imperviousness of the catchment area. That means if the surface is solid enough, then there will be no percolation and the water will be flowing over the surface as it is. And it may approach unity value if the area becomes fully impervious. But this equation cannot be rational because this runoff that not only depends upon the precipitation but it also depends upon the recharge of the basin as we have seen in the previous method. So that's why this is used for the minor purposes where the design of the storm water drains is used, or for the small water control projects, especially where the urban areas are located, because in the urban areas the percentage of impervious area is quite high because of the concreted area. Therefore, this method of computing the runoff, it is avoided for the rural areas or for the analysis of the major storms, because the calculation of the exact value of the K, which is denoting the relation between precipitation and the runoff, that is very tough. Because of that reason, this is avoided for the major storms. Moving on to the next method, that is the computation of the runoff by using the infiltration capacity curve. Now, what is this infiltration capacity curve? So it is the plot of the infiltration capacity against time. So this graph, which is shown as decreasing between the rainfall rate and the time, that is representing the infiltration capacity curve. This is the infiltration capacity curve, while the bar chart, that is representing the hydrograph. So what we do, this IC curve that is superimposed on the hydrograph, the resultant amount that represents the runoff, because this infiltration is the amount of water that is percolating into the ground. So if this water is percolating into the ground, the whatever amount of curve is available above the infiltration curve, whatever amount of hydrograph is remaining above the IC curve, that is representing the runoff volume. So the highlighted area, that is representing the runoff volume, because rest of the water has been percolated. So this infiltration, that is being shown with the dotted lines, while the runoff is shown with the hatched lines. Now this method can be used very easily if the rainfall rate, it never falls below the infiltration capacity rate. But it may not always be possible. It may be possible that this is the hydrograph at certain areas and the infiltration curve is like this. So in that case, what amount of water is going into the ground, that is very complex to calculate. So in this situation, there will be distortion in the capacity of the infiltration versus time, and it is generally assumed that the infiltration capacity at any time is determined by the mass infiltration that has occurred up to that particular time. So if a rain begins at low rate, that means initially the rate with which the rainfall was occurring, that was very low, and the rainfall during the first hour, that is contributing 2/3 of the infiltration, then the capacity at the end of the hour will be taken as the capacity that will be at the 2/3 time and not at the t is equal to 1 hour, because only the 2/3 portion of the rainfall is contributing towards the infiltration. So this can be used very easily, but there are certain problems in this method also. Moving on to the next one, this is the computation of the runoff depth by using suitable infiltration indices. Now we have already seen that the infiltration capacity curve determined on the test plot, it cannot be applied to large basins or for the heterogeneous areas where the rainfall is not constant or the rate is not almost along a similar line but is fluctuating very heavily. At an instant in large area, the infiltration capacity and the rainfall rate, they vary from point to point. Also the subsurface flow, that is the interflow, which is in the upper crust of the earth surface, that is also very substantial. Now when we plot the infiltration curve, it is not normally picked on the curve itself. So runoff volumes are generally computed for the large areas by using infiltration indices. And for this purpose, we are having two of the methods of the calculation of the indices, that is the W index and the phi index. What is this W index? So W index is the average infiltration rate or the infiltration capacity averaged over the whole storm period. So F is the total infiltration, that is including the basin recharge, called potential infiltration. P is the total precipitation, Q is the total runoff. So out of the total precipitation, if we deduct the total runoff, we will get the total infiltration. And if we divide this total infiltration by the duration of the total storm, that is the duration of the rainfall in hour, we will get the index as the W index. So if we already know the W index for a certain area and if we know the duration of the storm in that area, then we would be able to calculate the infiltration, that is W into TR. And from here, if we know the total infiltration already, so out of the total precipitation, if we deduct the total infiltration, then we will get the total runoff. So initially what we are doing from the previous data points, we would calculate this W index for a certain area. Once we have calculated this W index, based upon that, for the current storm that is happening right now, for that we would be able to calculate the infiltration value. And once we know the infiltration, then it is very easy to calculate the total runoff. The next of the index is the phi index. Now what is this phi index? So this is defined as the average rate of loss such that the volume of rainfall excess of the rate that will be equal to the volume of direct runoff. That means the rate of rainfall above which the rainfall volume is equal to the runoff volume. So this bar chart that is representing a typical hydrograph between the rainfall intensity and the time of the rainfall. This phi index that is representing a line, this phi index that is representing a line, that means below this rate, if a rainfall is occurring, that will be contributing towards the infiltration. So any bar that is below this phi index, that will be contributing completely towards the infiltration. So the bars that I am highlighting, that is representing the total infiltration is equal to the total precipitation, while in the rest of the bars there is certain portion which is above the phi index. So that is representing the rainfall axis. So this infiltration is represented by this dotted area, while this runoff is represented by the hatched area. And the duration for these bars, that is calculated as the period in which the rainfall axis is occurring. So that is TE1 plus TE2 plus TE3. In this way we calculate the phi index, and once we know the phi index for a certain area, then we would be able to calculate that how much rainfall is contributing towards the runoff. So in both the indices method, first of all we will calculate the indices based upon the previous data, and then using those indices value we will calculate the runoff for the current storm. Then the next method is the computation of the peak rate of the runoff by the rational formula. Now what is this? In the design of the hydraulic structures, sometimes the total volume of the runoff that is required, that how much water is contributing towards the runoff in cubic meters, and sometimes the peak rate is required. Now the method that we are going to discuss, that is the rational formula, that is giving us the peak discharge or the peak runoff value, and that is given by K into P into A, where K is the coefficient of runoff, A is the drainage area of the basin in hectares, and P is the precipitation for the duration of the rainfall greater than equal to T. Now what is this T? This is known as the time of concentration. Now what is this time of concentration? So let's say if this is a certain catchment area and this is the outlet point, that means each stream that is contributing the water to this point, ultimately the water from this entire catchment area will be coming out from this outlet point only. So the time taken by the most distant water droplet to reach the outlet point, that is known as the time of concentration, which is denoted by capital T or the capital TC. Both the notations are used. Now this equation that we have discussed as Q is equal to K into P into A, that forms the basis of the rational formula, which on the adoption of the appropriate desired units for the precipitation is given below. That is peak discharge, that is equal to a constant value, that is 1 by 36 into K into PC into A, where Q is the, or rather QP is the peak rate of runoff in Qmax, K is the coefficient of runoff which is obtained for the different regions differently, A is the drainage area of the basin in hectares. So because this is an empirical relationship, you have to keep in mind the units of the all the parameters. And this PC is the mean rainfall intensity in centimeter per hour for a duration which is equal to capital T and for a given frequency of occurrence. On the similar lines, there is one more formula which is calculated for the designing of the hydraulic structures, which was given by a scientist named Kerbich. So that is regarded as the Kerbich formula, and it helps us in evaluating the inlet time or the overland flow time. That means for how much duration the water was available in the catchment area, and this is given as T naught is equal to 0.885 into L naught cube by H, its whole power to the 0.385, where T naught is the overland flow in hours, L is the distance from the farthest, that is the critical point, to the outlet at the hydraulic structure in kilometers. In the previous calculation, we were using the time. In this relationship, we are using the L naught distance, which is representing the distance. H is the total fall in the level from the critical point to the outlet, and that is in meters. Now both these L and H, they are found out from the survey plan of the area, and based upon that, this T naught value can be easily calculated. And once we know the overland flow time, then we can calculate the runoff easily from the given discharge value. So from the discharge rate, if we multiply the overland flow time, we would get the volume of the water that was flowing over the surface. Now it completes all the methods through which we can compute the runoff. In the next video, we will look at the hydrograph and what are the different components of the hydrograph. Thank you.